Hello, good afternoon to all of you. So I'm Vineet Sharma, your mentor of mechanical engineering here. So as you know, your BEL exam is on 20th of December here. Okay, so today I'm here to give you some important questions related to the thermal engineering. Okay, so we are going to do 100 questions related to the thermal engineering branch, in which I am going to cover up the thermodynamics, some questions of the heat transfer, as well as the fluid mechanics part also. Okay, now. So before any delay here, so let us start with the questions here. So here is our first question. Which of the following statement is the false regarding the relation to the specific speed? Ns is equal to n root p h to the power 5 by 4. So first of all, this question related to the hydraulic machines here, and the specific speed parameter is very important in the hydraulic machines. Okay, which is specifically defined for the turbine as well as the compressor also. Okay, which is defined for the turbine as well as the pumps also. Sorry. Now in this case, we have a different formulas for the turbine and we have a different formulas for the pump also, that you have to remember. If we just see for the turbine, the formula is defined in this way: Ns is equal to n root p h 5 by 4. That is a formula for the specific speed in case of turbine. But if we see for it for the pump, the formula is going to be written as in the form of n root q h 3 by 4. Okay, well, now what does this tell you? The specific speed parameter is specifically used for comparing the different type of turbines as well as the different type of pumps here, which are operating under the same parameters here. Okay, now so let us suppose they are operating under the same, I can say, under the same head here or the same power here. Okay, so correspondingly, which is going to be the most suitable turbines here, which we can just mark that thing with the help of the specific speed here. Okay, now just read the relations here. The relationship is valid for both impulse as well as the impulse reaction turbine. So as we know, it is applicable for both of these turbine, and the formula is written as this one here. Okay, and we may have a different values of the turbine specific speed also. For example, if we just see for the Pelton wheel turbine, it is a high head turbine here. So in that case, the specific speed value is going to be very small. But if we just go for the, I can say, reaction turbine in this, in which we have a Kaplan turbine, let us suppose, which is a low head turbine, and that for that particular turbine, the specific speed value is going to be very large. Okay, now the next part, the value of the specific speed depend upon the system of unit. Yes, that is a correct statement here. Statement option number A, option number B, both are the correct one here. Why? Because whenever you are calculating the value of the specific speed, you have to make ensure that you use the correct unit of the specific, and you use the correct unit of the power as well as the head here. Okay, so in this case, you have to remember that whenever we are calculating the value of the specific speed, the n has to be put in the RPM here. The value of the P has to be put in the kilowatt here. Okay, and the value of the H should be in the meter form. That unit we have to use. You don't have to use the simple SI unit of the power while calculating the value of the specific speed. Coming back to the next part, the value of the specific speed for Pelton wheel will be lower than that for the Kaplan turbine. Yes, that is also a correct one here. Why? From the relationship, you can see the specific speed is inversely proportional to the head here. Okay, it is inversely proportional to the head. And the Kaplan turbine is a low head turbine, so corresponding value of the specific speed is very large. But if we talk about the Pelton turbine, the corresponding head is very large here, or I can say the specific speed value is going to be low in that case. Okay, next part, the dimensions of the specific speed are FLT minus 1. Okay, so it is not like that. First of all, that a specific speed are the dimensionless quantities here. Okay, the specific speed is having some dimensions also. If you just solve it, you are going to get the irregular, I can say, the dimensions here. Okay, but it is not like that FLT minus 1. And it is not like that it is a dimensionless quantity. Okay, so also remember that in this case, if you have to remember the dimensionless form of the specific speed, the formula will be written as n root p by rho divided by gh to the power 5 by 4 here. Okay, that is the dimensionless formula of the specific speed. Along with that, if we just see the formula of the specific speed for the pump here, the formula is written as n root q gh 3 by 4. That is the formula you are going to see. Okay, so therefore I can say out of these four options, which one is the false statement? Option number D will be the correct answer in this case. So that's a very simple question. Now coming back to the next question here. For a liquid beam pump, pressure head at the pump inlet plus velocity head in the suction pipe and minus vapor pressure head, it is equivalent to. Okay. Yes, what can be the answer in this case? So in this case, if you just see, you are going to get the PDF here, don't worry. The PDF will be shared to you in your group, don't worry. Okay, now? Next, for liquid being pumped, the pressure head at the pump inlet. Let us suppose point number 1 is representing the pressure head at the pump inlet. Okay. Plus velocity head in the suction pipe, that is Vs square by 2g, and minus vapor pressure head, PV by rho g. If you just pay attention very carefully, that is a formula of the NPSH, which we study in the pumps here. NPSH. What does the meaning of NPSH? Net positive suction head. It basically tells you that how much energy at the inlet of the pump is more than the vapor pressure head here. Why it is required? In order to avoid the cavitation at the inlet of the pump. Okay, so you have to remember the formula here. That is very, very important for you. And from the NPSH only we define the Thomas cavitation factor here. Okay, and in order to avoid the cavitation in the pumps, we have to make ensure that the energy or head available at the inlet of the pump, it should be more than the NPSH here. Okay, so always remember that. If we just see in the case of pump, the NPSH available at a particular location, it should be more than the required NPSH here. Okay, it should be more than the required NPSH here. That you have to remember. Okay, so in this case, option number B will be the correct answer. Option number B will be the correct answer. Yes. Next question. So here we have a next question. The figure given below show the relationship between the power discharge for a different vane exit angle of a centrifugal pump. In the figure given below, the curve C hold good for. The curve C. Okay, now just see. Actually, in the case of centrifugal pump, you are using the 3 different type of curves here. We have a backward blade. Okay, we are having the radial blades as well as we are having the forward blades here. So the different type of blades are classified on the basis of the vane angle at the exit. So for the forward blade, the angle phi is going to be more than 90 degree. Then we have a radial blade. Radial blade phi is going to be equivalent to 90 degree. Yeah, that you have to remember. And then we have a backward blade. For the backward blade, the phi is going to be less than 90 degree here. Okay. Now the most important thing which you have to remember in this case is that whenever you are talking about the pump, if you are using the forward blade, in that case you are going to get the maximum pressure rise in the pumps here, but the power consumption is also going to be significant. If you just see the graph here between the pressure and discharge, you are going to observe that at a constant discharge, the power consumed by the curve number C or the blade number C is going to be highest. That means it is a forward blade in which the vane angle is more than 90 degree. Okay. So power consumption is of the forward blade are going to be very large as compared to the radial blade, as compared to the backward blade. So backward blades are going to consume the least amount of the power among all of these here. And the next point is that if we talk about the pressure rise, the pressure rise of the forward blade is also very high as compared to the radial blade as compared to the backward blade here. Okay, and we also have to remember that in general the normal blades which we use in the reciprocating in the centrifugal pumps are the backward blade. Okay, and also remember one more thing, if nothing is mentioned in the question, okay, so you have to assume that we are using the radial blade in the case of centrifugal pumps. Okay, we are not using the backward blade there. So option number C is going to be the correct answer in this case. Next part. The process by which air inside the centrifugal pump is removed and filled with liquid to be pumped is called. Okay. Now what we are doing? What can be the answer here in this case? Yes, tell me the answer. Yes, the answer is going to be priming here. So priming is basically a process in which what you are doing, you are filling up the entire pump with the liquid here. Which liquid? The flowing liquid here. Okay, that you have to remember. And the next part is that in this case, what is the need of doing the priming? Let us suppose if some amount of air is present inside the pump. Okay, some amount of air is being present inside the pump here, and you are providing the energy into the pump here. Okay, the manometric head which you are providing, let us say it is equal to 100 meter. What is a manometric head? Manometric head is the head against which the pump has to do work. So in order to make ensure the water flows from the suction tank to the delivery tank, we have to provide that much amount of energy according to the theoretically we have to provide that much amount of energy there. Next part. Now, if air is present inside the pump here, in that case, you are going to see the pressure develop. The pressure develop is going in terms of the air here. Okay, so I can say that pressure rise will be equivalent to density of the air, that is 1, gravity I am assuming as a 10, and manometric head as 100 here. That you have to remember. Okay, now? Next part. So in this case, you are going to observe that we are having 1 kilopascal here. Okay, in this case. Now let us suppose if you are doing the priming. If you are doing the priming, the entire pump is going to be filled up with the water here. So if the entire pump is going to be filled up with the water, so I can say this manometric head is going to be in terms of water. In terms of water there. And in that case also, the pressure developed in the pump, it will be equivalent to the density of the water multiplied by gravity multiplied by the 100 here. Okay, so you are going to observe that we are having the 1000 kilopascal. Okay, so that means the 1000 kilopascal is required to lift up the water in the pump. But if air is present, only how much pressure is being developed? 1 kilopascal is being developed. So it is not sufficient to rise up the water from the suction pipe to the delivery tank here. Okay, now? So that is a priming here. That is why we have to do the priming here. Okay. Next part. Yes. Cavitation phenomena can take place in the Pelton turbine, reciprocating pump, centrifugal pump, and the tangential flow turbine. Okay. What is the meaning of cavitation? Cavitation is a phenomena. Okay. Whenever the liquid is flowing from a low pressure region, the formation of the bubble will take place. And as the liquid flows into the high pressure region, the bursting of the bubble will take place. So as soon as the bursting takes place, the void gets created. So those empty voids are being created by the surrounding fluid. And the surrounding fluid are going to be rushed to fill the void here. So in the process of this, what is happening? A pressure wave is being generating, which is flowing inside the tube here, or I can say inside the device, okay, and which may damage the surface of the wall also. So in that case, you have to understand that if we talk about the cavitation is taking place in the case of hydraulic turbines. Okay, specifically if I talk reaction turbine, it is taking place. Okay, in the pumps, it is taking place in the centrifugal pumps here. Okay, not in the reciprocating pumps. And why not it is not taking place in the Pelton turbine? Because in that case, the pressure is being constant here. Reciprocating pump, why it is not taking place? Because we are not taking a suction pipe as a very long. Otherwise, the negative slip will take place. Okay. So here in this case, option number C, that is centrifugal pump, will be the correct answer. Okay. So that's again a very simple case. Next part. In a centrifugal pump, the sum of the suction head and the delivery head is called as. The sum of suction head and the delivery head is called as. Now, what is the meaning of that? Actually, if you just see the simple pump here we have a delivery pipe. Here we have a delivery pipe. Here we have a casing, let us suppose, and here we have a suction pipe. Okay, and here we have an impeller. Over it, we have a blades here, like in this case. Now, what is happening? Now we have to suck the fluid into the suction pipe. How the liquid is sucking here? When the pump is rotating at a very high speed, the suction is being created at the inlet of the pump. So I am assuming, let us say, this point 1 is representing the inlet to the pump here. Okay. Now the water is not going to lift on its own from the bottom to the center of the pump. You have to raise the water from the bottom to the center. So for that purpose, you have to provide the energy. Okay, for that purpose, you have to provide the energy, and that energy is known as the suction head here. So I can say HS is representing the suction head here. Remember that. Next part. Now, in order to lift the water from the center of the pump to the delivery pipe, to the top of the delivery pipe, we have to provide extra energy, and that energy is going to be known as delivery head, which is represented by HD. Okay, so HD is representing the delivery head. So here you can see, in order to lift the water from the bottom to the top, we have to provide certain amount of energy which is known as Hs here. So Hs is nothing but it is representing the static head, which is a sum of suction head plus delivery head. Okay, but there is a problem because see water requires some energy to get flow from the suction from the bottom to the delivery tank here. Okay, so whenever the water is flowing in the suction pipe, if you just see the corresponding suction losses, or I can say frictional losses, are going to be there in the suction pipe as well as in the delivery pipe. So we have to provide extra energy, okay, to overcome the frictional losses in the suction pipe as well as the delivery pipe here. So I can say uh, static head, suction head we have to provide. Along with that, frictional losses in the suction pipe, we have to also provide that. Okay, along with that, we have to provide the delivery head. Along with that, we have to provide the frictional losses which are taking place in the delivery pipe. To overcome that, we have to provide extra energy. Okay, so if I provide that much amount of energy, the water will be flow from this particular position to the top position here. Now, in order to bring the water out of the delivery pipe, what do we do? What do we have to do? We have to provide extra delivery head also. So in that case, we also have to provide the extra delivery head. So you can see this entire energy which I am providing here, it is known as the manometric head here. This is known as the manometric head. Okay, remember that part. So in this case, what does the sum of suction head and delivery head represent? It tells you about the static head. Okay, what is manometric head? Manometric head is a head against which the pump has to do work. Manometric head is a head which the pump in which we have to provide the energy to the water so that it can flow from the bottom to the out of the delivery pipe here. Okay, so that's a required condition. Next part. Which equation clearly define the entropy change? Which equation clearly define the entropy change during the isothermal process for a system with m kg of gas at a pressure of P1, volume V1, temperature T1, and entropy S1? Okay. So what we are doing? Simply, I can say a process is taking place isothermally in which the properties are being changing from subscript 1 to subscript 2. Pressure, volume, I can say temperature and the entropy here. What can be the answer here? C. Okay. So first of all, you have to understand that when we are talking about the entropy change of a gas, we have different relation here. The first relation is written as Cp ln of T2 by T1 minus R ln of P2 by P1 here. That is the first relation. Either you can calculate the value of the entropy change with this relation also. Okay, or either you can use Cp ln of V2 by V1 plus R ln of P2 by P1. So these are the three relations which you have to remember. Okay, in order to calculate the value of the entropy change for an ideal gas. Okay, or for any gases here. Now in that case, you can use any one formula here because all of those formulas are going to give you the same answers. Okay, that you have to remember. Now in this case, first of all, just see, we are talking about the isothermal process. So if I use the first formula, the first term will become 0. If I use the second formula, the first term again will become 0. Okay, so how can you calculate the entropy change? Either you can calculate with this particular formula minus R ln of P2 by P1, either you can calculate with the formula of R ln of V2 by V1, or either you can calculate with this particular formula also. Okay, it's all depends upon you. So out of these three, you can see the option number C is the correct answer in this case. Okay, now, so that's again a very simple case. Next, which equation is applicable if there is heat input output or shaft work output input during the flow through the confined passage problem? So we have a problem of confined passage in which the fluid is flowing. Along with that, some work is being done. Along with that, some heat is being transferred here. Okay. So here you can see, if we talk about the first equation, Bernoulli's equation here in this case. Okay, Bernoulli's equation. In the case of Bernoulli's equation is representing the conservation of energy here. Okay, Euler equation is also representing the conservation of energy here. Steady flow energy equation is also representing the conservation of equation here. Conservation of energy here. Bernoulli equation is nothing but it is the integrated form of the Euler equation. Euler equation is a differential form here. Okay, and Bernoulli's and Euler both can be derived from the steady flow energy equation only. Okay, in defining the steady flow energy equation, we take the consideration of the energy interaction by means of boundary also, through the boundary also, which can be there in the form of work or it can be in the form of heat also. Okay, remember that part. So option number C will be the correct answer. Next, two process isobaric and isochoric are represented on a TS diagram. They are starting from the same point out of these processes which shall have a higher slope here. So that's a simple case. So value of the dt by ds for the constant volume process is, yes, what can be the answer here? Option number B. Yes. So isochoric. So for isochoric, we have a slope as P by CV. For a constant pressure, we are having a slope of T by Cp here. Okay, that we have to remember. Next part. If 1 meter cube of air at 10 kilogram per centimeter square is allowed to expand freely to a volume of 10 meter cube. So initially the volume is given to us 1 meter cube and finally the volume is given to us 10 meter cube here. Correspondingly, the pressure is 10 kilogram per centimeter square. What do you want to calculate? You want to calculate the work. What can be the answer? Okay, we don't have to find out the value now. We just have to check it is 0, positive, negative here. So if it is expanding, it is going to be 0 in this case. Why? Because the work is taking here the expansion is taking place freely. Okay. So if there is, it is not a throttling process. Yeah, it is not a throttling process. So if the expansion is taking place freely, you can see there is nothing to work against the system here. Okay, the piston doesn't have to do against anything work. The piston doesn't have to do work against anything. So correspondingly, it is a free expansion process, or I can say option number A will be the correct answer here. Don't confuse it with the throttling process. That is a different process here. Okay, now. Next. What is the value of the specific heat of the gas in an isothermal process? Yes, what can be the answer? What can be the answer in this case? The value of the specific heat for the gas in an isothermal process. Remember that we have a different values of the specific heat. For a constant volume process, we have a different specific heat. For a constant pressure, we have a different specific heat. Okay. For isobaric and isochoric, we have a positive specific heats here. But if you talk about the polytropic process, we have a negative specific heat. If we talk about an adiabatic process, okay. In the case of adiabatic process, you can see heat transfer is equal to 0. So I can say specific heat in the adiabatic condition is going to be 0. Similarly, if you have an isothermal process, isothermal condition, temperature change is going to be 0. So I can say specific heat is going to be infinite here. Okay, so option number B will be the correct answer. Next question. The fixed point for the Celsius temperature scale is our ice point, steam point, both ice and steam point. Okay. And option number D, triple point of the water as 0.01 degree Celsius here. Now, in this case, you have to remember that whenever we are defining the temperature scale, we have two types of temperature scales here. A simple temperature scale, which are used to measure the temperature. Then we have a thermodynamic temperature scale, which is used to define the temperature, or I can say used to measure the temperature. Along with that, which is having a 0 Kelvin temperature also. Okay. Thermodynamic temperature scale is known as the Kelvin scale. That you have to remember. Now, in the simple temperature scale, we may define different types of the scales here. Okay, like degree Celsius, Fahrenheit, Rankine, etc. You can also create your scale, or you can also create your own scale. Okay, and the calibration is generally done on on at the fixed point of ice point and the steam point. That you have to remember. It is not like that you have only 2 points. You may have a different points also. Like we have a sulfur point. Okay, we have a golden point. Okay, like that we have a different points here. Sulfur point is the boiling point of the sulfur. Okay, gold point is the freezing temperature of the oxygen here. Oh, sorry, boiling temperature of the oxygen here. So option number C is the correct answer here in this case. Next, work done in an adiabatic process between a given pair of end states depend upon the end states only, particular adiabatic process, the value of the index and the value of the heat transfer here. Yes, what can be the answer? Please mark the option question number also. Please mark the question number also here. I am not getting the exact answer for which question you are giving me the answer here. Please write down the question number also. 13th D. Okay. Let us start with the first law of thermodynamics here. The first law of thermodynamics for any particular process. Let us say the process is taking place from 1 to 2. From 1 to 2, the process is taking place. So if I have to write down the first law of thermodynamics here, you can simply say it can be written as Q12 is equal to U2 minus U1 here plus W12 here. Okay. So in this case, if the process is taking place adiabatically, the Q12 is going to be 0 or W12 is going to be written as U1 minus U2 here. So in that case, I can say the work is depending upon the change in internal energy, and change in internal energy is a property of the system here. It depends upon the initial and final state. Okay, it is depending upon the initial and final state. That is point number 1 and the point number 2. Okay, and you also have to remember that work is always a path function, but this is a special case in which the work can be considered as a point function also. Okay, so I can say in an adiabatic process, it is depending upon the end states only. Okay, why so? Because if we just see in the adiabatic process, from one single point, we can only create one adiabatic process here. You cannot create two adiabatic processes from a single point. That you have to remember. Okay. For example, if I define a point like this one, A point, and if I take two adiabatic processes passing through this point A, you are going to observe that it is violating the second law of thermodynamics. It is not possible. Why? Because if I close this two, if I just carry out a process here which is cutting down these two reversible adiabatic processes, you are going to observe the heat transfer is taking place only through the black color process. The heat transfer is not taking place through the red color processes here. Okay, now that you have to understand. So in this case, I can say it is violating the second law of thermodynamics. Remember that condition also. Now, coming back to the next question, which is true for a reversible polytropic process here? Temperature remain constant, entropy remain constant, or some heat transfer take place, or enthalpy remain constant here. What can be the answer? Question number 14. It is not Piyush, it is not depending upon the index n here. Remember that. Because just remember that reversible adiabatic process can be plotted in only single way here. Okay, now otherwise it will violate the second law of thermodynamics here. Which is true for a reversible polytropic process? 14 dB. Okay, now just see. Here we are talking about the polytropic process. First of all, in thermodynamics, whenever you're covering it, there are 5 processes we have to see: constant pressure, constant volume, constant temperature, polytropic, and adiabatically here. Okay, these are the 5 processes. And always remember that in all the 5 processes, we have to check for 5 parameters here. The change in pressure, change in volume, change in temperature, heat and work transfer. Okay. Polytropic process is the only process in which pressure, volume, temperature, as well as heat and work, all of these parameters are changing here. They are not equal to 0 there. Okay. So remember this condition. In the case of polytropic process, temperature may get changed, enthalpy may get changed, entropy may also get changed, and heat transfer is going to take place here. Either the heat addition is going to be there, or either the heat rejection is going to be there. Okay, so option number D will be the answer there. Next part. The work done during the expansion of a gas is independent of pressure if the expansion takes place isothermally, adiabatically in both the cases, or in none of the above cases here. Yes. What can be the answer of question number 15? The work done during the expansion of a gas is independent. First of all, if the expansion is taking place at a constant temperature isothermally here, the equation is going to be written as PV equal to constant. That means correspondingly the pressure and volumes are changing here. It is depending upon the pressure, it is depending upon the volume here. In the adiabatic also, the process is written as PV gamma equal to constant here. So I can say in both the options, okay, it is depending upon the pressure here. So therefore I can say none of the above cases will be the correct answer in this case. Okay, na? None of the above cases. In both the cases, it is independent of the pressure here. Just go through the formula of the work done here, you will get the answer. Just go through the formula. When heat is converted from one form to another, some energy is lost. As a result, the total heat provided to a system does not equal the work performed by the system. What can be the answer? A, B, C, D. Yes. A, B, C, D. Repeat. Just give me a second. Let me get back to the question number 15 here. Just see here. In the question number 15, we are talking about the isothermal process and adiabatic process. In both the processes, if you just go through the mathematical formula itself here, the isothermal work done is PV ln of pressure ratio. It is depending upon the pressure here. If you just go through the formula of the adiabatic case, P initial, V initial minus P final, V final. It is again depending upon the pressure only. Okay, now? Or from the equation itself, you can see. So if the expansion is taking place, the work done is going to be dependent upon the pressure here. Okay. Question number 16. What can be the answer? Question number 16. A. How it is following the Clausius statement of the second law of thermodynamics here? It is not following the Clausius statement. Clausius statement states that in order to transfer the heat from low temperature to high temperature, you have to provide the work input. Without any work input, you cannot transfer the heat from low to high temperature. That is a statement of the second. I can say Clausius statement of the second law. Okay, it is not following the second law here. Sorry, Clausius statement is not following here. The statement follows the first law of thermodynamics. That is also a wrong one here. Why? Because according to the first law, the net heat transfer into the system is going to be equal to the net work transfer here. Okay, it is not following this first law of thermodynamics also. Next, the statement has enough information about radiation. Irrelevant option is given. The statement depicts information about the zero law of thermodynamics. It is also irrelevant. Okay, so this question is basically wrong here. None of the options is correct here. You can mark this type of question as an objection. Okay. So this is, I can say all options are incorrect here in this case. It is following the Kelvin-Planck statement of the second law of thermodynamics here. Which one of the following statements applicable to a perfect gas will also be true for a irreversible processes here? Out of these three equations, which is applicable for the irreversible as well as reversible here, as well as for the perfect gas also? A, B, C, D. Tell me the answer. Yes, what can be the answer here? Option number C. Yes, option number C is the correct one here. Remember that whenever you are writing the first law of thermodynamics, let us say in this way, dq equal to dE plus dW. Okay, you have to remember that the first term on the left hand side, first term on the right hand side, it tells you about the system here. Okay, remember this condition. So if you have a du here, then I can say it is applicable for the closed system. If you have de here, it is applicable for the open system. That you have to remember. That is the first thing. The second term tells you about the process here. Remember this condition also. If you are having the dw, it is written for the irreversible as well as reversible both. It is applicable for both here. If you are having the pdv, okay, then I can say it is specifically written for the reversible process. So I can say from the first equation you can see it is written for the closed system as well as reversible process only. It is not applicable for the irreversible process. dq equal to tds, that is a wrong case, because for the reversible process ds is going to be equivalent to dq by t. That you have to remember. For the irreversible processes, ds is going to be more than dq by t here. That you have to remember here. Okay, now that is why we include a entropy generation term here. Okay, remember this condition also. Next part, TDS is equal to du plus PdV. All of these terms are the point functions only, so they can be, I can say, applicable for reversible as well as the irreversible processes here. Okay, because all these terms are depending upon the end states only. It does not depend upon how the process is being carried out. Okay, so option number C will be the correct answer. Next question. Which one of the following phenomena occur when gas in a piston cylinder assembly expand reversibly at a constant pressure? In simple language, it is just saying you constant pressure expansion process. Constant pressure expansion is a heat addition or a heat rejection process. Just tell me. Constant pressure expansion process is a heat addition or a heat rejection process. Constant pressure expansion process. Constant pressure expansion is a heat addition process. Okay, heat is added to the gas. Similarly, isothermal expansion process is a heat addition process. That you have to remember. Isothermal compression is a heat rejection process. Okay, so option number A will be the correct answer in this case. Next part. Which of the following is a false statement? False. No thermodynamic cycle can have the thermal efficiency of 100%. Yes, what can be the answer of this question? Option number C. No thermodynamic cycle can have thermal efficiency of 100%. That is a correct statement. Even if you just see, Carnot cycle is not having a 100% efficiency. Okay, it is also depending upon the high temperature and the low temperature here. That you have to remember. Next part, all reversible cycle operating between the same two thermal reservoir have the same thermal efficiency. That is a corollary of a Carnot theorem. That is also a correct one. Thermal efficiency of an irreversible cycle is more. It is wrong. It is less than the reversible cycle. So that is a false statement. Next part. Non-flow energy equation dq equal to du plus dw. It is valid for. Yes, tell me now the answer. It is applicable for the reversible, irreversible process. What can be the answer in this case? Option number C. How? Yeah, option number C. You are going to get this lecture for the CS also. Don't worry, yaar, Ankit. Next, it is going to be applicable for reversible as well as the irreversible processes here. Okay. If you have a PDV here, then it is specifically written for the reversible process. Next question. Which of the following statement is a corollary of a Carnot theorem? Simple question is there. Carnot theorem states that efficiency of all the reversible engine operating between the same temperature limits, okay, are going to be same one. That is a corollary of a Carnot theorem. What is the statement of the Carnot theorem here? Efficiency of reversible is always going to be more than the irreversible cycle. That is a statement of Carnot theorem here. Okay, so I can say which one is the correct answer? Option number A. Yes, the option number A will be the correct answer here in this case. So that's a simple case. Option number A. The dash statement states that heat flow from hot substance to cold substance unaided. Okay. Without any work input, the heat always flows from high temperature to low temperature. That is, I can say, indirect statement of the closest statement. Okay. Indirect statement of the closest statement. In order to transfer the heat in the reverse direction, you have to provide some work input. Okay. So option number A will be the correct answer. Next, work is considered to be a superior form of energy as compared to the heat energy. Why? Yes, what can be the answer? A, B, C, D. See, yes, while work is fully convertible into the heat here because it is a high grade energy. But if you talk about the heat transfer, it is not a high grade energy. It is a low grade energy which is consisting of available energy as well as the unavailable part. Okay. So option number C is the correct answer. Next part, what is true for the heat engine? Efficiency of all the engine is same. It is not a required condition. Efficiency of all reversible engine is same. That is also not a true statement here. Okay, why? Because we don't know what are the temperature limit in the second option. Efficiency of all the reversible engine working between the same temperature limit is same. That is a correct statement here. No? Option number C is going to be the correct answer here. So that's a simple case. Which of the following introduce the irreversibilities in the actual Carnot engine here? In the actual Carnot engine, yes. What can be the reason of irreversibilities inside the system? A option. See, whenever we talk about the irreversibilities are of two types, internal as well as the external here. And in the case of Carnot engine, we don't have any type of irreversibility here. We don't have internal irreversibilities. We don't have external irreversibilities here. First of all, you have to remember that. Now, they are providing you some information, some options here. So you also have to remember that whenever you are performing the Carnot engine, either you can perform the Carnot engine in the internal combustion here, or I can say in the external combustion. Okay, so there are two different ways you can perform the IC engine here, in the IC as well as the EC here. So if you are using the EC, in that case, we are having the four component boiler, turbine, condenser, and expander here. If you are using the, I can say, internal combustion, in that case, we have a piston cylinder arrangement. Okay. So if there is a mechanical contact between the piston and cylinder, so I can say there will be a friction also. So that will be a reason for the internal irreversibilities in the actual Carnot engine. Okay. Remember that condition, friction between the moving part. And also remember, sometimes they ask you that what are the assumption taken in performing the Carnot engine. So you have to remember that whenever we are performing the Carnot engine in the piston cylinder, the piston is assumed to be perfectly insulated. Okay, cylinder is assumed to be perfectly insulated, but cylinder head, this portion is not perfectly insulated here. For half portion, for adiabatic processes, it is going to be considered as a, I can say, insulated, but not for the other processes. Okay, for isothermal heat addition or heat transfer, it is not going to be considered as a adiabatic one. Okay, or I can say insulated one here. Next, which of the following is not a characteristics here? Not a characteristics of the entropy. It remain unchanged in all the adiabatic frictionless process. It change in all the adiabatic frictionless processes here. Yes, what can be the answer? What can be the answer in this case? What can be the answer? A, B, A, B, A, B, A, B. Confusion between A and B. First of all, just remember that entropy is representing the randomness here, okay, or the level of disorderness here. So let us suppose if you are providing the heat input into the system, the heat is a low grade energy. Whenever the heat is transferring through the boundary into the system, the corresponding entropy is always going to be increased here. Okay, that is a required condition. That is an important one. And also, if the heat rejection is taking place, in that case, the heat is taking away the some randomness here, some unavailability with it. So I can say along with the heat transfer, there will be an entropy transfer here. Okay. So you have to remember first, Whenever the heat transfer is taking place, if heat addition is there, and entropy is going to be increase. If heat addition is negative, the entropy change is also going to be negative here. Remember that conditions here. Okay, so let us see the first option. It remain unchanged in all the adiabatic frictionless process here. So here we are specifying the frictionless process, so I can say it is talking about the reversible process here. Okay, so I can say it is option number A is a correct one here, because reversible adiabatic process is a isentropic process. Okay, it change in all the adiabatic frictionless processes, that is a wrong one. Okay, it is a wrong statement here. It increases when heat is supplied irrespective of whether temperature changes or not, that is a correct statement. Okay, it decreases when heat is removed irrespective of whether the temperature changes or not, that is also correct here. Okay, because if the heat is removing, then the entropy is going to be decreased, because heat is taking away some unavailability with it. Now just give me one answer here. Let us suppose if you are having a process like this one. If you are having a process like this one, 1 to 2. Now tell me, is it a heat addition process or a heat rejection process? Just tell me the answer. Is it a heat addition or heat rejection process? 1 to 2. What can be the answer here? Heat addition or rejection? Heat rejection. Heat rejection. All the answers are wrong here. Heat addition. It is a heat addition process. Yeah. Remember that. Why it is a heat addition process? Even though the temperature is decreasing, okay, but it is a heat addition process. Why? Because the entropy is increasing here. This process is simply showing you that even though if you are carrying out a process, okay, heat is getting added into the system, but why the temperature is decreasing? Because the work which has been performed, it is it is much more, I can say it is larger than the heat transferred into the system here. Okay, so I can say the work which has been performed, it is due to the decrease in internal energy also. That is why the overall temperature is decreasing. Okay, so it is a heat addition process, not a heat rejection process. Next part. Which of the following is true for the process 1 to 5? This process. Yes, answer A, B, C, D. Constant volume. Yes, option number A. It is an isentropic process here. It is a graph between the temperature and entropy, not the pressure and volume. Okay. So PV gamma equal to constant is the correct one here. What is the correct expression for the heat transfer? Yes. What can be the answer in this case? What can be the answer in this case? 28 number question. Actually, what is happening here? See, from here we define the derive the closest inequality. Okay, so here we have some initial point. Here we have initial point. We are carrying out a process I to F. So this is our first process we have carried out. Okay. Now this process is being converted into the three different processes here. How? In this case, we are performing the first process I to A, then A to B, and then B to F here. Remember that in the thermodynamics, every reversible process can be converted, or I can say can be written in the form of the sum of three processes, out of which two are going to be reversible adiabatic and one is going to be isothermal here. So in this case, I to A and I can say B to F, they are representing the adiabatic process here. These are the adiabatic process. A to B is representing the isothermal process. Okay. So in both the processes, red and blue color, what we have done, we have just moved from initial position A to final position B here. Okay. So now you can see if I apply the first law of thermodynamics, for the red color process, I can say QIF is going to be equivalent to the change in internal energy plus WIF here. That is the first law of thermodynamics for the red color process. Okay. If I write down the first law of thermodynamics for the blue color process, I can write QIABF is equivalent to UF minus UI. In this way you can write. Now you can see in the question itself, area under IABF and area under IF, they are equal. They are equal, and we are drawing the PV diagram. So I can say area under the PV diagram is representing the work done here. So if the areas are same, so correspondingly I can write the WIF are going to be equivalent to WIABF here. Okay, so if I subtract these two equations, now in this case work done are same now. So I can say they will be cancel out. They will be cancel out. So therefore QIF is going to be equivalent to QIABF here. That's what you are going to get here. Okay now. So further I can write QIF is equal to QIA plus QAB plus QBF here. As IA and BF are the adiabatic processes, so these are going to be 0. So therefore QIF and QAB are going to be same here. So option number C will be the correct answer in this case. Okay, so from here you derive the closest equality. Next question. Next question is, a process occurs spontaneously if the entropy, so that's a simple case. Every natural process in the universe is basically increasing the entropy of the system here. So option number A will be the correct answer. Next, the temperature in a process in which work is done by expanding a gas under adiabatic condition will be. Okay, if you are carrying out an adiabatic process and if the work is being done during the expansion process here, what will be the temperature change? Is it going to be decrease, or I can say it is going to be negative or is positive here? What will be the effect on the temperature during the adiabatic expansion process? In the case of adiabatic expansion, the work is going to be, temperature is going to be decrease. Why? You can just calculate that from the first law of thermodynamics. Here you can see adiabatic process, Q is going to be 0. So I can say work is going to be equivalent to delta U, which will be final minus, which will be initial minus final here. Okay, so you are going to observe that if work is being done, work is positive, then initial internal energy has to be more than the final internal energy here. So in this case, option number A will be the correct answer here. Okay, na? Next part. Which of the following are thermodynamically irreversible? Irreversible here. Gradual heating of water from a heat source, isothermal expansion, mixing of two ideal gases. What can be the answer? What can be the answer here? Akshay, 27th number question. Just give me a second. Let me cover this question here. Let then move toward the 27th question here. Just don't worry. Okay. In this case, if you just see, we are gradually heating of the water here. Okay. Gradually heating of water is taking place through a finite temperature difference because we don't know whether the hot source temperature is high or low. So I can say it is an irreversible process. Heat is transferring through a finite temperature gradient. That is why. Isothermal expansion in a Stirling cycle, that is a reversible process. Okay. Mixing of two ideal gases is always going to be considered as an irreversible processes here. So you can see 1 and 3 are going to be the correct answer here. Okay. Option number D will be the correct answer here. 1 and 3. Statement number 2, isothermal expansion is going to be a reversible process. It is not an irreversible process. Remember that. And let us move toward the question number 27 first. Just give me a second, student. There's a problem in question number 27 now. What was the question number 27 here? Yes. Yes, what can... Answer is correct here. Option number A. The TS diagram is given to us. Temperature entropy diagram. It is not a PV diagram. Don't get the mistake here. That's why I have told you. It is not a PV diagram. It is a temperature entropy diagram. Okay, so vertical line is representing the isentropic process, reversible adiabatic process. Okay, let's move toward the question number 32 now. So here we have degree of disorder when two gases are mixed is 1 to 5 curve, that is an isentropic process. The degree of disorder is representing the entropy basically. So if you are mixing, the entropy is going to be increase. So it is going to be higher than that of individual gases here. Okay, now. Next question. Clapeyron's equation is used for finding out the. Now remember that we generally create a two plots here, the TP diagram and the pressure temperature diagram here. Okay, the TP diagram at a constant enthalpy, it is equivalent to it is known as the Joule-Thomson coefficient here. Just remember that part. Okay, if we talk about the DP diagram, dP by dt, it's simply written as the HFG divided by T here. Okay, or I can simply say, just give me a second. Clapeyron equation is written in this way. So remember the Clapeyron equation, it is generally applicable in the wet region here. So it is used to calculate the values of the specific volume, temperature, or the enthalpies, I can say. Okay, at any temperature and pressure in the wet region. Option number C will be the correct answer in this case. It is not applicable for the superheated cases here. Next, which of the following statement is correct? Pressure and temperature are independent during the phase change. Okay, let us see. Pressure and temperature are independent during the phase change here. It is not like that. Okay, first one is that pressure and temperature are dependent upon the phase change here. If you are defining a certain pressure, let us suppose if I define the 100 degrees Celsius temperature, we are having a defined vapor pressure at that line. We are having a defined saturation pressure at that point. Okay, na? Next, isothermal line is also a constant pressure line. That is a correct one. Isothermal line is also known as the constant pressure line here. If you just simply create a TS diagram here, you can see in the wet region, the constant pressure and the isothermal lines are same. Entropy decreases during the evaporation. That is a wrong one. Because during the evaporation, entropy is going to be increased. The term dryness fraction, that is a wrong one here. Because dryness fraction is a mass of vapor divided by the total mass, not the liquid mass here. It is also incorrect here. Okay, option number B is the correct answer here in this case. Don't mark the option number D as a correct answer. Next question. Regenerative heat exchanger, direct contact type heat exchanger. Okay. Conduction through a cylindrical wall. First, conduction through a spherical wall is a hyperbolic curve. It is a hyperbolic variation here. Okay. Conduction through a cylindrical wall is a logarithmic variation here. Direct contact type heat exchanger, in which hot and liquid fluid are making direct contact with each other. So that is a water cooling tower. Regenerative heat exchanger, in which you are using the matrix. So practical example is L Youngstown air preheater. Okay, these are the preheater here. These are the preheater. Remember that. Where do you use that preheater? In the gas turbine power plant. You also have to remember that condition also. Okay. So I can say 2143. Option number D. Option number D as a correct answer. Option number D as a correct answer here. Okay, na? Next. Drop-wise condensation is a liquid condensate collects in. What can be the answer here in this case? Remember that whenever we study the condensation are of two types. The first one is a film condensation and the second one is a drop-wise condensation. So during the starting of the condensation heat transfer, always the drop-wise condensation take place. What is the meaning of drop-wise? Here we have a surface which is having a lower temperature than the surrounding fluid. So as the fluid is making a contact with the surface, the drops get condensed over the surface. The condensation began and the droplet starts to form over the surface here. Okay. But due to the continuous, I can say, droplet condensation, a time the state will achieve that we have a formation of a film-wise condensation here. Okay. Generally, the drop-wise condensation is most accurate here. I can say it is better here as compared to the film condensation. But over the period of time, always the drop-wise condensation does not does not be present here. It is always get converted into the film-wise condensation. Okay. So you have to remember the droplets are the liquid are going to be collected in the form of droplets and they are not going to wet the solid here. Option number A will be the answer here in this case. Next part. They are not going to wet the solid surface. Remember that. After the prolonged time here, what happens? The large number of droplets get formed and it will convert into the film-wise condensation here. Then it is going to wet the surface here. Okay, not in the previous case. Next, in a current carrying conductor, if the radius of conductor is less than the critical radius, so that's a simple case. If it is less than the critical radius, what you are going to see? That by adding the further insulation, the heat transfer is going to be increased. Okay. So I can say with the higher heat transfer or a higher heat loss, large amount of current can easily flow through the wire. So option number B will be the correct answer in this case. So that's a simple one. Which of the following statements are correct for a black body? A black body continues to emit radiation even when it is in thermal equilibrium with the surrounding. That is a correct one here. Okay, it is a perfect emitter, ideal absorber here, ideal emitter or perfect absorber here. A black body is a perfect emitter. That is also a correct one here. Absorptivity alpha is equal to 1, represent a black surface. That is also a correct one here. Okay, so I can say option number C is going to be the correct answer. Next question. Absorptivity depends upon the wavelength of an incident radiation wave. Emissivity is dependent on the wavelength of the incident radiation wave. Yes. A, B, C, D. What can be the answer here? A, B, C, D. Does the absorptivity and emissivity depends upon the wavelength or not? क्या लगता है आपको? Option number C. Both 1 and 2. Yes, both 1 and 2 are the correct one here. Okay, remember that in the case of a gray body, the emissivity is not depending upon the wavelength here. And according to the Kirchhoff law, when the thermal equilibrium has been achieved, the emissivity is going to be equivalent to the absorptivity only. Now, both of these parameters changes, or I can say depends upon the wavelength of the radiation waves here. So, option number C will be the correct answer in this case. Now, next. According to the which concept, the propagation of thermal radiation take place in the form of discrete quanta called as photon. Each quanta has an energy of E equal to hv. Yes, what can be the answer? Option number A. Yes, it is a Max Planck quantum theory here. Okay. Next. Fraction of radiative energy leaving one surface that strike the other surface is called as. Yes, answer. The fraction of the radiation energy leaving the one surface and striking the other surface here. It is a radiative flux, view factor, or anything else. That's a simple case here. It is a view factor. View factor is also known as the shape factor. Shape factor is also known as the configuration factor here. It is a shape factor here. It is a configuration factor here. Remember that. So option number C is going to be the correct answer in this case. Okay, now. Next question. Which one of the following statement is correct? The non-dimensional parameter known as Stanton number is used in which case? Yes, tell me the answer. A, B, C, D. A, B, C, D. What can be the answer here? Option number A. Force convection heat transfer in flow over a flat plate here. Yes, always remember that. First of all, the Stanton number is defined as the ratio of Nusselt number divided by Reynolds into Prandtl number. Okay. In the case of a forced convection here, flow over a flat plate, we study a Reynolds-Corbin analogy, which basically make a bridge between the fluid friction and the heat transfer coefficient here. Okay, or like I can say convection heat transfer here, in which according to the Reynolds-Corbin analogy, Stanton number, Prandtl number to the power 3 is equal to Cfx by 2. So over the flat plate at any particular location, you can calculate the value of the local drag coefficient by using the experimental formulas here. So once you know the value of the drag coefficient, you can simply calculate the value of the heat transfer coefficient with the help of Nusselt number, okay, which is defined in this Stanton number. So I can say this number is specifically defined for the forced convection over the flat plate here. Option number A will be the correct answer. Next, Prandtl number of a flowing fluid greater than unity. So that's a simple case. That's a simple case now. So you have to remember this particular formula. So now you can see if the Prandtl number is having a value greater than 1, the correspondingly delta is going to be more than the delta T. So therefore I can say the hydrodynamic boundary layer thickness is going to be more than the thermal boundary layer thickness here. Option number A will be the correct answer. Yeah, you are going to get the PDF, don't worry. I am going to share the PDF in your group, don't worry. Okay, and it is already there in your portal. All the PDFs have been attached in the portal here. In your panel, you are going to get all the PDFs here, don't worry. Next, which of the following is an example of forced convection? Chilling effect of cold wind on a warm body, that is a wrong answer. Flow of water in a condenser tube, that may be the answer. Cooling of billet, that is a natural convection. Heat exchange on cold and warm pipes. Now just see. In this question, option number B and D, both can be the correct answer here. Okay, but most efficient, most effective one will be the option number B here. Okay, now in the case of B here, because in the case of condenser, if you just see, the condenser is a device which has been normally used in the power plants, or I can say in the refrigerator here. And in that case, the fluid of flow is taking place with some certain velocity, and there we are having the forced convection there. Okay. Next part, the parameter responsible for the loss of heat from a hot pipe surface in a room without fan would include, yes, tell me the answer in this case. Temperature of the surface and air, emissivity of the surface, and length of diameter of the pipe here. First of all, in this case, you have to understand that if a pipe is placed in a room, in that case, the heat is going to be transferred by means of a convection here or by means of radiation here. So if the heat is taking place through the radiation heat transfer, then we may have a emissivity also. If the heat transfer is taking place by means of free convection, then it is depending upon the temperature as well as the length and diameter of the pipe here. So option number D will be the correct answer here, all of the above. Next, on a summer day, a scooter rider feels more comfortable while on the move than while at a stoplight. So that's a simple case. Why? Because due to the motion, the more heat is going to be lost. Okay, now more heat is going to be lost by convection here as well as the radiation. Option number C. Okay, option number C will be the answer there. Next, dash number is a connecting link between the velocity and the temperature field, and its value strongly influence the relative growth of velocity and thermal boundary layer. That's a simple case. Which number is directly linking the hydrodynamic boundary layer with the thermal boundary layer? That is a Prandtl number. Okay, option number C. Option number C is going to be the correct answer, not option number A. Next, the use of dissipative light forces. The use of dissipative light forces for reducing the random motion, and therefore the temperature of the small particles also, typically atoms or ion, is called as. In which of the cooling phenomena you are using the light in order to reduce the motion of the atoms and molecules here? So that is a part of a laser cooling here, in which you are using the laser light here. Okay, now option number C is going to be the correct answer here. Next, film coefficient is a ratio of. So that is not a thing which you cover in the heat transfer subject, but it is a part of a condensation heat transfer. In that case, film coefficient, which is defined as a H here, it is defined as the ratio of the K by the thickness of the condensation layer here, film condensation layer. So I can say it is defined as the ratio of thermal conductivity to the equivalent thickness of the film of the fluid here. Okay, you can skip that part. You can skip that part here. It is not important for you. Next, in order to achieve the maximum heat dissipation, the fin should be designed in such a way that it should have a. Okay, now just see what are the meaning of fins. Fins are defined as the extended surfaces over the surface to enhance the heat transfer. Okay, to enhance the heat transfer rate. Now you have to understand, if we have a fin like this one, okay, now in this fin also, if you just see, if I see the first half, this is the first half of L by 2 length, this is the second half of the L by 2 length. Okay, you have to observe very carefully. In the case of fin, large amount of heat is being transferred, large amount of heat is being dissipated from the first half here as compared to the second half. So what I am trying to say, the total amount of heat which is being dissipated from the fin, it is going to be equivalent to Q1 plus Q2. And in the length, if you just see the lengthwise, so first half of the length rejects most of the heat as compared to the second half. Okay, that means the additional use of the material on the second half is not going to, I can say, benefit you. Okay, now it is not rejecting large amount of heat as compared to the first one here. So in that case, as per economical point of view, if you just see, maximum lateral surface at the root side of the fin is most efficient as compared to the later half. Okay, that we have to understand. So option number C will be the correct answer. Next, in the convection heat transfer from hot flue gases to the water tube, even though the flow may be turbulent, a laminar flow region exists close to the tube. The heat transfer through this film take place by convection, radiation, conduction, both convection and conduction here. What can be the answer? What can be the answer in this case? Remember the condition that whenever the fluid is flowing in the turbulent region, we have a very small layer adjacent to the solid surface in which I can say a laminar sublayer is formed. Okay, and in the case of laminar sublayer, you have to understand that we assume that the velocity varies linearly here. Along with that, the heat is transferring through the conduction here. Okay, now because the thickness of the laminar sublayer is so much small that we don't consider the movement of the I can say the atoms or molecules here. So correspondingly, the conduction is taking place in the laminar sublayer region here. Okay, and how do you quantify the laminar sublayer? We have a formula of 11.6 kinematic viscosity divided by shear velocity here. What is shear velocity? Under root of maximum shear stress divided by density, average velocity divided by F by 8 here. So that is a formula of the laminar sublayer. Next part, a fin will be necessary and effective only when. Okay, what can be the answer in this case? 52 number question. What can be the answer? Remember that if we talk about the fin here, effectiveness is defined as the ratio of Pk by Ha here. Okay, so from here we see that effectiveness is directly proportional to the conductivity, directly proportional to the P by A ratio, inversely proportional to the heat transfer coefficient. So larger the value of the thermal conductivity, larger will be the effectiveness. Larger will be the ratio, larger will be the effectiveness. Larger the heat transfer coefficient, less will be the effectiveness here. So we have to make ensure that the fin should be used in such a way that its thermal conductivity must be large and correspondingly heat transfer coefficient must be small here. So option number B will be the correct answer here. Okay. Next, a sphere, cube and a thin circular plate, all made of the same material and having the same mass. They are initially heated to a temperature of 250 degrees Celsius and then left in the air at room temperature for the cooling. In which of the following are going to be the correct answer here? Okay. So here we have a sphere, here we have a cube like in this way, and here we have a thin tube. So a thin circular plate like this one here. Okay. Now if we just see, if they are left in the room at a room temperature, which mode of heat transfer is going to be dominant here? Convection mode of heat transfer is going to be dominant. Free convection, I can say. Okay. And in this case, the sphere is going to lose its heat slowly here. Why? Because all the heat are going to be concentrated toward the center of the sphere here. So I can say the heat transfer is going to be there fast in the circular plate, then in the cube, and then in the, I can say, sphere. Okay. So if you just see the options, all will be cooled at the same rate, that is a wrong one. Circular plate will cool at a lowest rate, that is a wrong one here. It will cool at a faster rate here. Sphere will be cooled faster, that is also wrong one here. Okay. Sphere, but slower than the circular plate, that is a correct one here. Sphere is going to have a lowest rate as compared to the circular plate there. So option number D will be the correct answer. Okay. Next part. Solid cylinder at a steady state. How the conduction and the convection resistance are going to vary? So that's a very interesting question. First of all, if you just see, here we are talking about a solid cylinder here. Okay. And in order to compare the conduction resistance of a solid body, solid cylinder, to the surrounding convection resistance, we have a Biot number. Okay. So if you just see, we have a Biot number in this case, which is defined as the ratio of conduction resistance by convection resistance here, or which can further be written as HD by K. Okay, that is a formula here. Now in this case, what is D? D is representing a ratio of volume by area. So if I calculate the value of the volume of the cylinder, that will be pi by 4 d square h. If I calculate the value of the lateral surface area, that will be pi d h here. Okay, so now you can see characteristic dimension is nothing but it is equal to diameter upon 4 here. Diameter upon 4. Okay, so in this case, I can say the Biot number is going to be equivalent to HD by K. Okay, so if the diameter is increasing, correspondingly, what is happening? Conduction resistance is going to be increased and the convective resistance is going to be decreased here. Yes, now you are going to see the increase in conduction resistance while decrease in the convection resistance here. Okay. So option number A, not a B. Option number A is going to be the correct answer here. Now, conduction resistance is going to be increased. Next question. A 20 millimeter thick plate of iron is in contact with 2 millimeter thick plate of copper, making a composite thickness of 22 millimeter here. The heat will flow from copper to iron, not a required case, depend upon the temperature difference. So I can say yes, option number C is going to be the correct answer. The heat is going to be transferred. Yes, option number B. Let me just give me a second. In this case, first, the heat is going to be transferred from high temperature to low temperature only. Okay, so option number C will be the correct answer. Now, you are talking about question number 54 now. Just give me a second. Now just see. Yeah, what I have told you, that Biot number is basically used to compare the conduction resistance of the solid body with the convection resistance here. That is a case. Okay. And as we know that if the value of the conduction resistance is very, very negligible, at that point of time, the Biot number will become very, very small. And there we assume the lumped parameter analysis here. Lumped analysis here. Okay, that is a correct condition. Now, what is the formula of the Biot number? It is HD by K. What is D here? Characteristic dimension, which is given by volume by area. Volume by area here. So let us suppose if you have a cylinder like this one, which is having a diameter D, and let us say it is small d, and this is H here. Okay, you are going to see pi by 4 d square h pi dh here. So you are going to get the value of the characteristic dimension as small d by 4 here. Okay, small d by 4. So in this case, if you just see, you are going to get a formula of hd upon 4k. Now, if you are increasing the diameter of the cylinder, then what is happening? What is happening in this case? The corresponding conduction Biot number is going to be increased. That means conduction resistance is going to be increased here. Okay, don't get confused with this. That's a simple part. I can say previous analysis of the heat transfer. I can say starting analysis of the heat transfer here. Here we are not talking about a hollow cylinder. We are talking about a solid cylinder here. Okay, so you have to use the concept of Biot number, not a simple formula of logarithmic variation here. Okay. Next part. For conduction through a spherical wall with a constant thermal conductivity and with inner side temperature greater than outer wall temperature, what is the type of temperature distribution? That is a simple case. Hyperbolic is going to be the variation here. Next. Two insulating material of thermal conductivities K and 2K are available for lagging up pipe carrying a hot fluid. Okay. If the radial thickness of each material is same, now, first of all, just see, we have to use this material for the insulation purpose. For the insulation purpose, okay. So in order to use it as an insulation, we have to make ensure that the lower thermal conductivity material should be placed over the pipe here, over the cylinder here, so that the heat transfer should be, I can say, should decrease here. Okay, always remember that part. So in this case, I can directly say material with lower thermal conductivity should be used for the inner layer. What happens if you use the higher thermal conductivity material? The temperature drop will be larger. Okay, the heat transfer will take place from the cylinder to the inner insulation here, but it is going to be trapped in between the inner and outer. Okay, so option number B is the correct answer here. Next part. Which of the following lead to the reduction in the thermal resistance? In conduction, reduction in the thickness of the material and increase in the thermal conductivity. You can see L upon Ka. So decrease in thickness and increase in thermal conductivity is going to increase the thermal resistance here. In convection, stirring of the fluid and cleaning the heating surface, that is also going to decrease the convection resistance here. Heat transfer is going to be get efficient. In radiation, increasing the temperature and reducing the emissivity, that is also a correct one here. Okay, because if you just see the surface emissivity here, reducing the emissivity, that is the wrong one here, na? Actually, that word is a wrong one here. It is not a reducing the emissivity here. If you are increasing the emissivity, correspondingly the resistance is going to be less here. Okay, option number A and B will be the correct answer here. Option number A and B will be the correct answer both here. Okay. Next part. Thermal conductivity of non-metallic amorphous solid with decrease in temperature. So you have to remember that thermal conductivity for a non-metal is directly proportional to the temperature. So if the temperature is decreasing, thermal conductivity will also get decrease here. Okay. In case of metallic, they are inversely proportional to each other. So option number A will be the correct answer in that case. But here B will be the correct answer. Next, a diathermic wall permits the heat transfer by. Remember that when we talk about the heat transfer can take place through the adiabatic wall. It can take place through the diathermic wall. Adiabatic wall simply means Q is going to be 0. There won't be any heat transfer. In the case of diathermic wall, heat transfer may take place by any mode of heat transfer there. By any mode of heat transfer there. Okay. Next, metal and gas respond rapidly to a temperature change as compared to the non-metal and liquid due to the, first of all, how fastly the system is reacting to the surrounding temperature. It is being checked by with the help of a thermal diffusivity. Thermal diffusivity is defined as the ratio of K by rho Cp. So if you just see, for the metals, generally the value of the thermal conductivity is very, very large here. Okay. But for the gases, the value of the densities are also very, very less here. So due to the high value of the thermal diffusivity, they are going to react faster here. So option number C will be the correct answer. Next, heat pipe is widely used nowadays because heat pipe is a device which is having a very high value of the thermal conductivity. So it acts as a superconductor here. That is why we use a heat pipe for transferring the heat. Next, minimum thermal diffusivity is of aluminium, iron, lead here. So out of the 4 options, you can directly see rubber is going to be the correct answer here. It is a non-metal. Okay, now it is a non-metal here. Next, in which one of the following material is the heat energy propagation minimum due to conduction heat transfer here? Lead, copper, water, air. It doesn't require any explanation. Air is having a very low value of the thermal conductivity. Okay. Next, the speed of sound in a fluid is given by. So speed of sound is having a 2 different formulas, RT and C equal to gamma RT. Okay, it can also be written as dP by d rho here. How the density is being changing with the change in pressure. Okay, depending upon that, we have a different formulas of the speed of light. So generally, under the adiabatic conditions, we have a formula of root gamma RT. Under the isothermal condition, we have a formula of root RT here. Okay. If nothing is mentioned, you have to mark the option number B as a correct answer there. Next, a shock wave which occur in a supersonic flow represent a region. So basically, shock wave is a region in which there is a sudden change in pressure, temperature, as well as the density of the gases here. Remember that condition. That is an important part. Next, in fluid modeling of a flow pattern and a body submerged in a fluid, the non-dimensionless number that has to be kept to be same in the model and prototype. The first thing is, what is prototype? Prototype is representing the actual structure here. What is model? Model is representing the replica here. Okay. So always remember that in order to create the similarity between the model and prototype, we have to use the Reynolds number here. Okay. Under which case? Under the submerged case here. In the case of open flow, you have to use the Froude number here. Okay. Next, what is the principle of similitude? First of all, according to the principle of similitude, the testing can be done on the model and the result can be transferred from the model into the prototype here. Okay, so you have to create a similarities between the model and prototype. There are 3 different types of similarities here. What are those similarities? Dynamic similarity, we have a kinematic similarity, we have a geometric similarities here. Okay, remember this condition. So I can say option number B will be the correct answer here. Designing the model so that result can be converted to the prototype here. Next, according to the Buckingham pi theorem, the number of dimensionless group, remember that according to the dimensional analysis, in order to find out the proper dimensions, we have 2 different methods here. The first one is a Rayleigh method. The second one is the Buckingham pi method here. Okay. Rayleigh method is generally used when the number of unknown variables are 3 to 4 only. If you have a number of unknown variables more than 4, you have to use the Buckingham pi theorem. Okay. Let us say in that case, if you have a n number of variables here, n is representing the total number of variables here, m are representing the total number of fundamental dimensions here. In that case, n minus m groups are going to be formed here, which are going to be considered as a dimensionless group. Okay, so n minus m pi numbers are not going to have any dimensions here. Remember that condition. Okay, so option number C will be the correct answer in this case. Next, if K is the height of roughness projection and delta is the thickness of laminar sublayer for a pipe surface to be hydraulically smooth. Remember the condition. While doing the analysis of a turbulent flow, you classify the pipe as smooth pipe and the rough pipe here. Okay, so here we take the ratio of the K by delta. If the value of K by delta is 0.25, we say it is a smooth pipe. When the value of K by delta is in between the 0.25 and 6 here, we are having a transition pipe. If the value of K by delta is going to be more than 6, we are having a I can say rough pipe here. Okay, you have to remember these conditions here. These are very, very important for you. So option number A will be the correct answer in this case. Next part, what is chord flow? Chord flow is a flow, okay, remember that, which is taking place between the two surfaces here. One of the surface should be one of the surface should move with a constant velocity here. That is a required condition. One of the surfaces has to be moved with a constant velocity here. What are the practical example of chord flow? That is the bearings. Okay, the bearing which we are using in the industries here, these are examples of the chord flow here. So option number D is the correct answer there. Next part. In a flow through a pipe, the transition from laminar to turbulent flow does not depend upon. Okay. So transition from laminar to turbulent is depends upon the value of the Reynolds number. Reynolds number is defined as dV rho by mu. Okay. So from the formula itself, you can directly answer the questions here. You can see it is not depending upon the length of the pipe here. It is depending upon the velocity, density, as well as the diameter here. Okay. So option number C will be the correct answer here. Next, which of the following statement is correct while using the boundary layer equations here? Boundary layer equation can be used anywhere. It can be used only outside the boundary layer, can be used only inside the boundary layer. First of all, you have to remember that Bernoulli equation is representing the conservation of energy here. Okay, that is an important condition. Second thing is that what are the assumptions here? The flow is going to be steady, incompressible, a rotational flow has to be there. Okay, and flow should be along a streamline here. Now, if you just see inside the boundary layer, we are having a viscous effect. Okay, we are having a viscous effect, and due to the viscosity, we are having a rotational flow where you cannot apply the Bernoulli's equation. That is why we say that Bernoulli equation can only be applicable outside the boundary layer, not inside the boundary layer here. Okay, so option number B is going to be the correct answer. So that's a simple case. Next, for a fluid flow, according to the boundary layer concept, separation is going to occur when the. That is a very important question here, because you have to remember the conditions in the boundary layer separation here. The boundary layer separation can be checked by seeing the value of the velocity gradient. Remember that. If the value of the velocity gradient is going to be positive, then we say that we have a attached flow. Okay, when the value of du by dy become equal to 0, that means it is on the verge of separation here. Remember that part. And when the value of du by dy at y equal to 0 become negative, it is a detached flow, or I can say the flow has been separated there. Okay, remember the condition. Now you can see flow separation occurs when the pressure falls to 0, pressure rises sudden and rapid. Okay, different boundary layer comes across a sharp turn. That is the wrong one here. When the boundary layer of the fluid becomes stationary. So at the bottom of the surface, at the near to the surface, when the momentum of the flowing fluid, or I can say the fluid layer, become equal to 0, at that point of time the du by dy, the velocity gradient, will become equal to 0 there. So correspondingly the flow is going to be separated here, and the separation is going to be occur. So option number D will be the correct answer in this case. Next question. which shear stress distribution is the correct one corresponding to a flow through a pipe of circular cross section with a parabolic velocity profile? Okay, remember the conditions here. First of all, in the case of laminar flow, you are having a parabolic velocity profile. In the case of turbulent flow, you are having a logarithmic velocity profile here. Okay. If we talk about the shear stress profile, shear stress, remember that in the case of laminar as well as in the case of turbulent, you are having a linear variation. You are having a linear variation in the case of laminar as well as in the case of turbulent here. That is an important one. Okay, so I can say option number B is going to be the correct answer. At the center, you are going to have shear stress as a 0. At the top, you are going to have shear stress as a maximum there. Okay, remember the conditions here. Next part. When a fine hole is made with a pin at a point 2 on a working siphon as given in the figure, which of the following is most unlikely to happen? Unlikely to happen here, which cannot take place. First of all, just see, if I create a hole at this particular point, there is a very less chances that the fluid is flowing out of this point number 2. Why? Because the point 2 is at the some height here. Okay, and as a opening is there, in that case the air is going to be sucked into the pipe here. So as the air gets sucked into the pipe, correspondingly you are going to observe that first of all, option number B, air sucked into the pipe at point 2, it may take place. Second, as the air is sucking into the pipe, at the output you are going to observe the water coming out with the bubbles here. Okay, next part, due to the bubbles coming out of the siphon, the mass flow rate is also going to be reduced. Okay, so I can say option number A is going to be the correct answer in this case. Water leaks at the point 2 out of the pipe is most unlikely to happen here. Unlikely to happen here. There is very less chances here. Next, the line which gives the sum of pressure head, datum head and kinetic head of a flowing fluid in a pipe with respect to some reference line here. With respect to some reference line is going to be known as, remember that in the fluid mechanics you normally create two important lines, energy gradient line and hydraulic gradient line. Okay, energy gradient line, total energy line, both are the same thing. It represents you the sum of pressure head, kinetic head and potential head here. Okay, so option number B is going to be the correct answer here. Hydraulic gradient line tells you about the piezometric head here at different points. Next, if L1, L2, L3 etc. be the length, D1, D2, D3 etc. be the diameter here, okay, and capital L and capital D are the dimensions of an equivalent pipe. Okay, what are the required conditions then? Remember that what is the meaning of equivalent pipe? First of all, the multiple pipes can be connected in a series connection to increase the length of the pipe here, or I can say to transfer the liquid from to a large distance here. Okay, but if we talk about the parallel connection, it is generally used for increasing the discharge through the pipe here. Now, in order to convert the multiple pipes into a single pipe of uniform cross sections here, we use a equivalent pipe here. In the case of a series connection, the relationship between the dimensions of equivalent pipe and the compound pipe is written in this way here. Okay, na? Remember that condition. Option number D will be the correct answer here. Option number D will be the correct answer here in this case. Next, in order that the flow take place between the 2 points in a pipeline, the differential pressure between these 2 points must be more than the. Remember the condition that whenever the fluid is in flowing condition here, there are 3 energy associated with it. What are those energy? Pressure energy, kinetic energy and the potential energy. Okay, and you also have to understand that whenever the fluid is flowing, there is some friction also. That means the fluid must have sufficient energy to overcome the friction here. Okay, so which energy is generally used to overcome the friction? The pressure energy is generally consumed to overcome the friction here. That is why we have a negative pressure gradient in the fluid flow. Okay, so you can see the pressure difference must be more than the frictional force, surface friction and the viscosity here. So option number D, all options are going to be the correct answer here. Next, the head loss in case of hot water flow through a pipe compared to cold water flow will be. Okay. First of all, what is the formula of the head loss? Head loss formula is written as FL square upon 2GD, or you can write 32 mu U bar L upon rho G D square if I assume to be laminar flow. Remember the condition also. This formula is applicable for the laminar as well as the turbulent flow. This formula is applicable only for the laminar flow. That is a required condition for you. Okay. Now you can see HF is directly proportional to the viscosity. So larger the viscosity, larger will be the head losses here, larger will be the friction here. Okay. And we also know that in the liquids, the viscosity is inversely proportional to temperature here. That means if the temperature is being increased, viscosity is going to be decreased here. If the viscosity is decreasing, so I can say head losses are going to be decreased here. Okay. So you can say the head losses is going to be less in case of hot water as compared to the flow of cold water here. Okay. So option number C will be the correct answer in this case. Option number C will be the correct answer here in this case. Next, in which of the following situations siphon is generally used? What is siphon here? Siphon are generally used to transfer the liquid from one reservoir to the another reservoir, which are being separated by a hill here. Okay, so if you have to supply the water from one reservoir to the another reservoir, and in between you have a height here, in that case you have to use a siphon. Okay, and also remember, at the top of the siphon, what is the problem? There can be a problem of a cavitation also. So I can say option number A will be the correct answer here. Next, frictional head losses in a turbulent flow through the pipe is. Okay. Here student makes the mistake here many times. So just make ensure that okay, this formula is applicable for the laminar and turbulent flow. So whenever this type of question is being asked that how the frictional head losses are varying with the velocity. So whenever you have to check for the laminar flow, always just see this particular formula. Okay, just see this particular formula. Because if you are using this formula, you may get an idea that in the case of laminar flow also, head losses are varying with the square of the velocity, but that is not a case. Because in friction factor also, we are having a Reynolds number. Okay, now? So you have to understand, in the case of laminar flow, the head losses are directly proportional to the velocity here. And in the case of turbulent flow, you can see head losses are directly proportional to the square of the velocity here, V square here. Okay, remember this condition, this is important for you. Next, in a series pipe applications, what are the required condition? Always remember that in the case of series pipe application, the total head losses are going to be added up. Why? Because the frictional contact is going to be increased and the total discharge is going to be remain constant. Okay. But if you have a parallel pipe connection, in that case, the head losses are going to be same. Why? Because at the inlet and outlet of both the pipe, the reservoir difference is going to be remain same here and the discharge are going to be added up. So I can say in the series pipe application, the head losses are going to be added up to obtain the total head loss. That is a required condition here. Okay, na? So option number A will be the correct answer in this case. So that's again a very simple case. Next, flow pipe system can be said to be equivalent when the following quantities are going to be remain same. Remember that whenever you have a composite system like this one and you want to replace it into a equivalent pipe concept, okay, you have to make ensure that you just compare the head losses here and you compare the discharge here. So these two pipe must have a same head losses, these two must have a same flow rate also. That is a required condition here. So for the head losses, we have to make ensure the frictional losses are same and for the discharge we have to make sure flow should be same here. Option number A will be the correct answer here. Next, which of the following losses is not a minor loss? So that's a simple case. From the option itself you can see option number D is going to be the correct answer here. So that's a simple case. Next, in an isentropic flow between the 2 points, what is the meaning of stagnation? What is the meaning of stagnation here? See, stagnation properties are basically acting as a reference point. Okay, they are acting as a reference point to represent the total energy of a fluid at a specified point here. You may have a stagnation pressure, you may have a stagnation enthalpy, temperature, density, etc. here. Okay, it's all up to you. Generally, the stagnation properties are generally are used in the compressible flow here to define the total energy content at a specified point here. Okay, na? So I can say the stagnation pressure, temperature, density, they are going to remain constant here because they are acting as a reference point. And how do we calculate the stagnation properties? By assuming that the fluid has been isentropically deaccelerated to a zero velocity here. Okay, so if the fluid is not flowing, is not deaccelerating isentropically, it is not a case of stagnation here. Okay. Okay, don't worry. You will get us one session on the electrical also. Don't worry. Okay, na? I will send the message to the team here. Don't worry. Next, Reynolds stresses may be defined as. What are the meaning of Reynolds stresses here? Now just see. In the case of turbulent flow, if you want to calculate the various stresses here, there comes the different scientists here. They have given their own theories here, and according to their theories, the total stresses are basically a sum of the viscous shear stress due to the viscosity plus shear stress due to the eddies here. Okay, that we have to remember. The viscous shear stresses are being calculated with the help of Newton law of viscosity. That is a required condition. But the formula of the eddies viscosity is not defined here. We may have a different formulas corresponding, I can say, depending upon the different scientists here. Okay, so here we say that eddies viscosity are due to the fluctuating velocity components here. What are the meaning of fluctuating components? Fluctuating component simply means the instantaneous velocity of each atom and particles, each atoms and molecules in the water here or in a fluid here. Okay. So it is representing the additional shear stresses due to the fluctuating velocity components in a turbulent flow. The option number B, C is going to be the correct answer here. That's a simple case. Okay. Next, the Lagrangian description of a fluid flow is more computational because, why so? Remember that whenever you are doing the analysis here, we are having the two type of system description approaches here. The first one is the Eulerian and the second one is the Lagrangian here. Okay, and remember that in the case of Lagrangian approach, what we do, we take a single fluid particle and we analyze the fluid particle over the period of time here. Okay, so you may visualize in that way. If you have a simple pipe, let us say, in that case we may have a different atoms and molecules here. They are having a random motion also. So we have to collect large number of data here. We have to track the large number of data here over the period of time. So that is a very cumbersome approach here for the liquids here. But if we go for the Eulerian approach, what does the Eulerian approach do? Eulerian approach simply define a control volume like this one here. The control volume is defined in this way. Now, with which property the fluid is entering and with which property the fluid is exiting, that comes a part of a Eulerian approach here. Okay, remember this condition. So I can say Eulerian approach is generally useful for the fluid study. Lagrangian approach is useful for the solid mechanics study here. Okay, so in the Lagrangian approach, it is required to track the movement of a large number of fluid particles over the time here. Next question. One of the observations made by O. Reynolds in the 1883 is when the velocity of the flow was low, the diafilament in the glass tube was randomly distributed here. That is a wrong one here. Because when the velocity of the flow is low, then we are going to have a laminar flow. So if you are injecting a diafilament, it is not going to be randomly distributed here. When you are increasing the velocity of the flow, there may be a chance the diafilament get mixed up here. Okay, so now you can see Option number B is also wrong one. The straight line of the diafilament parallel to the glass tube was the case of laminar flow. That is a simple correct option here. With further increase of velocity of the flow, the diafilament failed to produce the shear stresses. That is a wrong one also. Okay. Next, in a flow measuring device, what is the meaning of velocity head? What is the meaning of velocity head here? Velocity head is simply representing you the, I can say, kinetic energy per unit weight here. It is representing as a dynamic head here, which is having a formula of V square by 2G. So in terms of the flow measuring device, we may say the free fall of the liquid. Okay, the height through which the liquid is freely falling and it is attaining a same velocity freely here. That is known as the velocity head. That is a definition of the velocity head in terms of fluid mechanics here. Option number C. Next, from a tank, a fluid is flowing out as a jet through an orifice. Okay, if H is the head under which the fluid flows out as a jet at vena contracta, and acceleration to gravity is g. In that case, what does root 2gs represents here? The root 2gs is representing the theoretical velocity here. Okay, just remember that part. So in this case, we have a formula of 2gh as a theoretical velocity. Okay, we are having an actual velocity as a cv root 2gh here. So there are two formulas here. Okay, the theoretical velocity and the actual velocity, which you have to remember. Next, pitot tube. What does the pitot tube measure? So now remember that whenever you are studying the pitot tube are of two type also. We have a simple pitot tube. We are having a, I can say, static pitot tube here. Static pitot tube here. Static pitot tube is also known as the Prandtl tube here. Okay. The simple pitot tube measures the stagnation head here. It measures the stagnation head. But if we talk about this static pitot tube, it measures the dynamic head here. Okay, remember that. It directly, static pitot tube directly tells you the difference between the stagnation head minus static head. Okay, because we have two openings in the static pitot tube. But in the case of simple pitot tube, we don't have a two openings. There we calculate the value of the stagnation head here. Okay, remember this one. So we require an additional manometer also. We require an additional manometer in the case of simple pitot tube to measure the, I can say, static head here. So after measuring the stagnation head and static head individually, you have to do the calculations and you get the value of the velocity of the fluid flow, or I can say the dynamic head here. So out of these four options here, I can mark the option number A as a correct answer, but it is not also a accurate one here. Okay, but out of these four, you can mark it as an answer here. Next, which of the following are the assumptions of the Bernoulli's equation? There is a loss of liquid while flowing. That is not assumption here because we don't assume any viscous effect here. There is no external force except the gravity acts on the liquid here. That is a correct statement. That is a correct statement here. Because we are considering only two forces. The first one is a gravity force and second one is a pressure force. Gravity is the only external force which is acting over the liquid here. Okay, remember that part. Now, the velocity of the energy of the liquid particle across any cross section of the pipe is going to be uniform. That is a correct one here. Okay, so option number B and C are going to be the assumptions of the Bernoulli's equation. Next, which one of the following statement is the correct for a force vortex? In that case, which one of the following statement is the correct for a force vortex here? So first of all, you have to remember what is the meaning of vortex flow? It is a rotating mass of a liquid. Rotating mass of a liquid. Now we may have two type of vortex here. The first one is a force vortex and the second one is a free vortex here. So if we talk about the free vortex, we have to understand the V into R is going to be remain constant. In the case of force vortex, V upon R is going to be remain constant here. Okay, remember the conditions here. Now, we have to mark the correct for a force vortex. It turns in an opposite direction to a free vortex. It always occurs in conjunction with a free vortex. It has a linear velocity directly proportional to the radius here. So I can mark the option number C as a correct answer. You can see from this part, V is directly proportional to the R here. Okay, now V is going to be directly proportional to the R here. Next, when a liquid rotates at a constant angular velocity about a vertical axis as a rigid body, the pressure, okay, remember that part also. If the liquid is rotating, okay, in that case, it is a case of a vortex flow. And if I take two random points, let us say point number A and point number B, you are going to observe these 2 points are at a different radial locations and at a same height. Okay. Now, as the liquid is rotating, the centrifugal forces are going to be act in the radially outward direction. So, in order to counteract the centrifugal forces, the net force it has to be act in the inside direction here, in the radial inward direction here, and that is known as the pressure force. So, in order to have a pressure forces in the radially inward direction, we have to make ensure that pressure at point B, it must be larger as compared to the pressure at point A here. Okay. And if you just see the formula, dP is equal to rho V square upon R into dr plus rho G dz here, you are going to observe that pressure difference is equal to half rho V square there. Okay. So correspondingly, I can write half rho omega square into R square. So I can say the pressure difference is directly proportional to the square of the radial distance here. So option number A is going to be the correct answer here. Okay, option number A is going to be the correct answer. Next, the condition for the length of convergent part and the length of divergent part. So that is a simple case. Generally, the length of convergent part is always going to be less than the divergent part here. Okay, because there can be a chance of energy losses in the case of divergent part here. So we have to increase the length in order to reduce the pressure losses. Next, which of the following is not an ideal instrument to measure the pressure here? Pressure gauge, inclined manometer, piezometer, all of those are the pressure measuring devices here. So option number C will be the correct answer. Okay. Next, why do we use a venturimeter? To measure the flow. In which direction you can use? In any direction you can use it. Okay. Either in the horizontal, vertical, inclined, in any direction you can use this particular device here. So that's again a very simple case. Yes. What are the forces being considered in the Navier-Stokes equation? Remember that Bernoulli's equation, gravity and pressure force are considered. Navier-Stokes equation, gravity, pressure and the viscous forces are considered. Reynolds equation, gravity, pressure, viscous and turbulency forces are being considered. So option number A will be the correct answer in this case. So that's again a simple question. Bernoulli equation is applicable when it is a steady, a rotational, incompressible, non-viscous. Yeah, that is a correct one here now. Yes, option number A is going to be the correct one here. Okay. Next, which of the following hydraulic machines are subjected to the cavitation here? So that's a simple question. We have already seen that. Reaction turbine and the centrifugal pumps are the devices which are subjected to the cavitations here. There is no problem of cavitation in the case of impulse turbine, and there is no problem of cavitation in the case of reciprocating pumps also. Okay. Okay, so it's been 2 hours here, and we have successfully done the 100 question related to the thermal engineering part here. Okay, now. So I hope it's very clear to all of you that all the questions here. So if you have any doubts in the questions here, please you can message me on the WhatsApp group. Okay, and I will just take your queries here. And the next part is that remaining session has already been done by the Rajiv sir here. Okay, the industrial part he has taken here, the production part is already been taken here. So just go through the recordings here, okay, and just to do the practice session, continue, just to do the practice question regularly here. Okay, now. Okay, so that's it for today's class here. So thank you very much. Yes, but which one here? Which was the following? See, in the case of reciprocating pump, I have already told you that we have a suction, the length of the suction pipe is not so much large here. That is why we don't have a cavitation here. If you increase the length of the suction pipe, there may be a chance the cavitation can take place, but generally the length of the suction pipe kept as a very small as compared to the delivery pipe. Next part is, in the impulse turbine, why don't we have a cavitation? Because impulse turbine is always operated at a constant pressure here. There is no change in pressure here. Okay. But in the case of reaction turbine, if you just see, as the fluid is flowing through the various components, the pressure is continuously decreasing. Okay, from the casing to the guide blade to the runner here. In the case of centrifugal pump, as the fluid is flowing inside the impeller, the pressure is decreasing. After that, the pressure is increasing here. So I can say at the inlet of the centrifugal pump and at the exit of the reaction turbine, there may be a chance of the this one here, cavitation here. Okay, now. Convergence section is having a less, just see, first of all, actually what happens here, in the case of a Venturi meter, why do we have a convergent divergent section? To vary the pressure and velocity here. So if you just see, in the convergence section, pressure is continuously decreasing and the velocity is increasing here. So as the fluid is flowing toward the divergence section, there will be a sudden change in the pressure here. So let us suppose if the length of the divergent portion is less, then what will happen? In that case, there will be a sudden rise in pressure which will lead to the eddies formations here. Okay, so we have to make ensure that separation does not take place, eddies losses should not be there. That is why we prefer the large length of the divergent pipe, so that there will be a gradually increase in pressure here. There won't be any sudden increase in pressure. Okay, so these are all of the things which we have to cover in this part here. Okay, so just do your revision very carefully. Okay, and start solving as much as possible number of questions here. That then only you are going to complete your revision part. Okay, now. Okay, so that's it for today's class here now.